Hey everyone. So in our last video, we talked about how to kind of create a graph by breaking the rules of linked lists and trees and just kind of having edges or infinity children, right? And also allowing relationships to go any way we want. So we can have lower nodes get connected to upper nodes. And so we lose all meaning of upper and lower and hierarchy and levels, right? We just have nodes connected to nodes. Now, there's a lot of other ways to represent a graph. And so to kind of explain how that works, rather than having the node know about all of its own edges, what we could do is say class graph. And so init. And so when we have a class, when we have a graph class, that's basically the collection that owns the nodes. And in this, we can choose to store things like a list of edges and a list of vertices or nodes. So if you think about self.edges as a list, and you also think about self.vertices, T-I-C-E-S, and that'll contain nodes. Then, we have kind of the initial stages of a graph. And then if you wanted to do something like self.add edge, then def add edge, and then pass in self. What you'll want to do is say self.edges .append. And then you can either reference by like their ID. Let's say that there's some rule in this graph that says we can't have duplicate numbers. And so we know that this data will be somehow unique. We're just pretending here. So you could append either a reference to the node. So 1 and 2 are now connected, and they're not necessarily connected in any particular way, as in it's not 1 to 2 or 2 to 1, it's 1 and 2 are connected. So this is a directionless edge. DIR. That's a directionless edge, and it allows us to have one node and another node be connected with no concept of which way they are connected. And so that's very useful. And then if we wanted to say stuff like def add node, add node and then the node itself, then we can still say self.vertices.append node. And now we have the ability to add nodes to our graph without them actually being connected, right? So we could call graph.addNode, right? And I'm just going to delete this. So we could call graph.addNode. Let's say that this is our space for our graph. And so when we add a node, let's say that we create a node 1 in here, and then we create a node 2 in here. If we call add node, we've just sort of added the nodes to our graph. And until we call add edge, right, our graph is a disconnected graph. So that's okay. That's part of the rules of graphs. You can have a disconnected graph. You can have a graph that looks like this. This is a valid graph. It's just called a disconnected graph. There's no way to get from one to the other graph, other nodes in the graph. If your graph contains any partition in it like this, where there's no way to get, from this graph to like this graph, right? It's a disconnected graph as well. So this graph has the property of being disconnected. So that's something that when you are representing a graph, if it has the possibility of being disconnected, you'll need to kind of have adding edges and adding nodes be separate. When we wrote a binary tree, we didn't have that. We had the notion of adding a node to a binary tree. Its place in the graph is automatically determined by its value. So in order to add a node to a binary tree, we go to a certain point and we create a specific edge in that place and link those two nodes. You can't have a binary tree that is a disconnected graph because it's not really a binary tree at that point. But if you want to have a graph where, like, for instance, Twitter is a very disconnected graph. There's all islands of communities that no one follows and no one out in them follows anyone else. And so you can have disconnected graphs in a graph and they're still valid. Now, how you would literally traverse this graph, we'll talk about that in the next video.